Jai Hind students, welcome to my YouTube channel. Students, the secret of success is sweat, but the taste of success is sweet. Again I repeat students, the secret of success is sweat, but the taste of success is sweet. And students, believe me, in order to have sweet taste of success, you need to toil very hard. You need to do that extra bit of hard work. You need to have that dedication. You need to have that zeal, that enthusiasm. You need to have that killer instinct that should come from within yourself, right? And believe me, with hard work, everything in this world is possible, right? So students, with that note, let's begin this session. In this particular lecture, I'll be concentrating on the topic of force experienced between the two straight, parallel, infinite long current carrying conductors. And we'll discuss two cases over here, where the current in the parallel conductors are flowing in the same direction, and then when they are flowing in the opposite direction. In both the cases, we'll try to find out the expression for the magnetic force which the two conductors exert upon each other, and then we need to find out the nature of the force as well. And by doing this article, we are going to define the SI unit of current, which is ampere, and this will be the standardized, internationally accepted definition of the SI unit of current, which we'll be discussing, right? Anyway, let's start with the topic then. So our topic is, we need to find out the expression for the force experienced between two straight parallel infinitely long current carrying conductors, right? And we are doing with case 1. Let's deal with case 1, that is when current flows in the same direction, both the wires. So let us consider these two with the long straight infinitely straight conductors, current carrying conductors, and let us consider these two wires be placed in air or vacuum. They are placed in air or vacuum. This is conductor 1, suppose, and this is conductor 2, right? And let us consider the separation between them is R. This is the separation between them. And as for the first case, the current through both these two infinite long straight conductors are assumed to be flowing in the same direction. So suppose the current flowing through this conductor is I1 and the current flowing through the second conductor is I2. Right? This is the case. Let us consider 2 points. This is point A and let us consider this to be point B. Now students, let's find out the expression for the force which they exert upon each other. Right? Let's consider conductor 1. So, due to conductor 1, the magnetic field B1 at point B is, this is a current carrying conductor, as we are aware through the magnetic effects of current that whenever we consider a current carrying conductor, magnetic field is established around it. The direction of it is given by right hand thumb rule, isn't it? So due to this first current carrying conductor, the magnetic field at point B will be directed inwards. And the strength of the magnetic field will be, B1 is the magnetic field at point B due to the first current carrying conductor, right? It is mu naught I divided by 2 pi r. This is the formula which we have derived using Biot-Savart law, isn't it? And it is directed inwards. Look, apply this rule like this. So, the magnetic field is directed inwards at point B. So, let it represent by this. This is B1 vector. And directed inwards like this. It is directed inwards. So, obviously, the second current carrying conductor will be perpendicular to this magnetic field, isn't it? B1 is directed inwards like this. And the second carrying current conductor is like this. Okay. Now students, this second current carrying conductor is under the influence of this perpendicular magnetic field. So therefore it will experience magnetic force. given by IL vector cross B vector. In the previous lecture, we have derived the expression for the magnetic force experienced by a current carrying conductor under the influence of magnetic field. So, the second conductor, that is the conductor 2 under the influence of magnetic field B1 will experience a force given by, okay, let us consider it to be F2. In vector form, it will be given by current flowing through the second conductor is I2, L. This will be the current element of the second conductor. L is any length of the second conductor. This portion may be considered to be length L, isn't it? Cross, what is the magnetic field? It is B1, under the influence of which is conductor 2. So, cross B1. Clear, students? Simple. Now, this is the cross product. Always remember it. And what about the angle between these two? I2L vector is like this, and magnetic field due to this first conductor at point B is directed inwards. So, the angle between the current element and the magnetic field B1 is 90 degree. So, in magnitude, it would be equal to I2L B1 sin 90. Sin 90 is 1, so simply B1 I2L, isn't it? So, F2 in magnitude, it will be given by, substitute this value of B1 from this equation. So, what do you get? Mu naught, this will be I1, this is the magnetic field at point B due to the first conductor. In the first conductor, current I1 is flowing. So, mu naught I1 divided by 2 pi r multiplied by I2L. Clear, students? So, F2, small f2, let us consider it to be the force per unit length. Its SI unit would be Newton per meter. Small f2 is force per unit length. So, it will be given by mu naught I1 I2 divided by 2 pi r. Clear, students? So, you can put this as equation 1. So, this is the expression for the force experienced per unit length of conductor 2 under the influence of conductor 1. Clear? Now, this is the magnitude of the force experienced, and this is the magnitude of the force experienced per unit length. As I have told you, it is the force per unit length. So, the SI unit of small f2 would be Newton per meter. Clear? Now, this is regarding the magnitude. Now, what about the direction, students? In the previous lecture, we have discussed the direction of the magnetic force whenever the current element is perpendicular to the magnetic field is given by Fleming's left hand rule. And there, I've told you a very simple method to remember this rule. I've told you FBI, it's a simple analogy. FBI. You need to stretch your left hand such that the thumb, the forefinger and the central finger all are mutually perpendicular to each other. Then if the thumb represents force, the forefinger represents magnetic field B and the central finger represents current I, FBI, right? So here current is along this direction, magnetic field is directed inwards. So let's check the direction of force F2, FBI. Look, this indicates magnetic field, so it's in the inward direction. The central finger represents the direction of the current. It will be like this. So the thumb is pointing towards left, isn't it? So this is where the direction of the force will be. This will be the direction of F2 vector. All are perpendicular to each other. B1, remember, it's in the inward direction. So this is the direction of magnetic field, this is the direction of the current element, and this is the direction of the magnetic force experienced by the second conductor. All are perpendicular to each other. So I think this is pretty clear, right? Okay. Now what we'll do is, we'll consider magnetic field at point A due to the second current carrying conductor, right? So, due to conductor 2, what we do is, due to the second current carrying conductor, the magnetic field B2 at point A, right? Now this is a current carrying conductor, this conductor is carrying current I2. Due to this current carrying conductor, magnetic field will be established at point A as well, the direction of which would be given in the outward direction. Apply this rule. The fingers are along this direction. The direction in which the fingers curl, that will give us the direction of the magnetic field. So here if you draw a tangent, it will be in the outward direction. So due to this current carrying conductor 2, the magnetic field at point B would be directed outwards. So if inwards is directed like this, then outward would be directed like this. This is B2 dot. You remember this symbol, no? Cross, it represents direction of magnetic field perpendicular and directed inwards. Dot represents the direction of the magnetic field perpendicular to the plane and directed outwards, right? So here the magnetic field at point A is like this, it's in the outward direction. So due to conductor 2, the magnetic field B2 at point A is given by B2 is equal to mu naught. What is the current flowing through the second conductor? It's I2. 2 pi r. R is the distance. Clear, students? Now, this first current carrying conductor is under the influence of magnetic field B2. So, the conductor 1 under the influence of magnetic field B2 will experience the force given by F1 is equal to I1L cross B2 vector. I hope it's pretty clear. So now let's try to evaluate it. This is length I1L is the current element of conductor 1. Now the current element is along this direction. Magnetic field B2 is along this direction, perpendicular and in the outward direction. So what's the angle between the current element and the magnetic field B2? It's 90 degree. So what we get is F1 vector in magnitude, it would be equal to I1L B2 sin 90. So what we get is B2 I1L. Therefore, F1 in magnitude, it would be equal to, substitute the value of B2 from this expression over here. So what do you get? Mu naught I1 I2 divided by 2 pi r L. So this is the force experienced by the first conductor due to the magnetic field at point A due to second current carrying conductor, right? So what is the force per unit length then? As I have told you, force per unit length is F1 divided by L. So what we are left with is mu naught I1 I2 divided by 2 pi r. So we have obtained the same expression. So put this as equation number 2. So from 1 and 2, it follows that from 1 and 2, it follows that force per unit length F1 is equal to F2 is equal to F say. It's constant and it is equal to mu naught I1 I2 divided by 2 pi r. So as I told you, this is not the force, this is the force experienced per unit length of the conductor. So its SI unit would be Newton per meter. So whatever force per unit length is being exerted by conductor 1 on conductor 2, the same force is exerted by conductor 2 on conductor 1, right? So magnitude wise it's exactly the same. Now let's find out the direction of F1. So for that, students, I have told you, whenever a current carrying element is perpendicular to the direction of the magnetic field, then the magnetic force experienced by it, its direction can be given by Fleming's left hand rule, FBI, right? So here, this is the magnetic field. So it is in the outward direction at point A, it's in the outward direction. Central finger is the current, so it's in the upward direction like this. This is the magnetic field outward, right? This central finger points towards the direction of the current. So this thumb points towards the direction of F1. So it is directed towards right. So therefore, the direction of F1 at point A may be indicated in this particular manner. Like this, F1 vector. Clear, students? So what's the conclusion? What's the overall conclusion? Whenever we consider currents flowing in two straight infinitely long straight conductors, and if the current in the conductors are flowing in the same direction, then they tend to exert an attractive force upon each other. The nature of the force is attractive. The nature of the force is attractive. Always remember. In case, in both the conductors, the current flows in the same direction, the nature of the force existing between them is attractive. This is the first point. Second point is, students, they form action-reaction pair. Just now we have discussed F1 is equal to F2, or force per unit length of the first conductor is equal to the force per unit length of the second conductor, isn't it? In magnitude, both are equal. But they are oppositely directed. So it means that they form action-reaction pair. They form action-reaction pair. That is, whatever force is exerted by conductor 1 on conductor 2, the same force is being exerted by conductor 2 on conductor 1. So these are the two very, very important conclusions, right? So students, we are over with case 1. That is, when the current in the two straight conductors flows in the same direction. Now let's concentrate the other case, second one. Okay, now we will consider the two straight parallel infinite long conductors in which the currents are flowing in the opposite direction. The currents are flowing in the opposite direction. So let's try this. It will be done in a similar manner, right? So these are the two straight conductors. Let's consider this to be the first conductor, and let us consider this to be the second conductor. These are two straight infinite long parallel current carrying conductors. Suppose current I1 is flowing along this direction. In the second conductor, current is flowing in the opposite direction. So I1, I2. Got the difference between the previous article and this article? You're dealing with this article now, when the current flows in the opposite direction. And obviously, the distance between them is considered to be R. And these two conductors are assumed to be placed in air or vacuum. This is considered to be point A. This is considered to be point B. Right? Okay, let's proceed then. Let's consider conductor 1. Conductor 1 carries current I1. Due to this I1, magnetic field will be established at point B, the direction of which would be in the inward direction, like this. Right? So magnetic field at point B will be directed inwards. So it can be shown like this. This is B1 vector and directed inwards. So students, magnetic field at point B due to current carrying conductor 1 is B1. What's the formula? Mu naught I1 divided by 2 pi r. Clear, students? This is the formula. And what about the direction? It's directed inwards. At point B, it is directed inwards. No doubt regarding this. Now students, look. The second current carrying conductor is under the influence of this perpendicular magnetic field. B1 is directed inwards like this, and the second current carrying conductor is like this. So the second current carrying conductor under the influence of magnetic field B1 will experience a magnetic force, right? So conductor 2 under the influence of magnetic field B1 will experience a force given by F1 or F2 rather. We are considering the force experienced by conductor 2. In vector form, it is given by I2L vector. This is the current element of the second conductor. Cross, it is under the influence of magnetic field B1. And both are perpendicular to each other. So the angle between them is 90 degrees. Sin 90 is 1. So we get F2 in magnitude, it will be equal to I2L B1 sin 90. Sin 90 is 1, right? So magnetic field at point B is directed inwards and current is along this direction. So sin 90 gets 1. B1, substitute this value B1 over here. So what we get is F2 is equal to mu naught I1 I2L divided by 2 pi r. This is the expression for the force experienced by the second conductor, right? So what about the force per unit length then? It will be F2 divided by L. So as I told you, small f2, it is force per unit length. So its SI unit would be Newton per meter, right? So it will be equal to mu naught I1 I2 divided by 2 pi r. Put this as equation A. Now let's obtain the direction of F1, students. Let's obtain the direction of F2 actually, right? So look, magnetic field at point B is directed inwards. Current is in the downward direction. So we need to find out the direction of F2 using Fleming's left-hand rule. Remember FBI, Federal Bureau of Investigation, right? FBI. Magnetic field, it is directed inwards. This is current, central finger. It is directed in downward direction like this. So what about the thumb? Thumb is pointing towards right, isn't it? So here the force would be, this is point B. So here the force would be along this direction, towards right. This is F2 vector. All are perpendicular to each other. All are perpendicular to each other. All are perpendicular to each other. This is the direction of the magnetic field. This is the direction of the current. This is the direction of the force. All the three are perpendicular to each other, right? So I hope you have understood this. Now let's consider the other scenario. Now consider second current carrying conductor, this one. Due to this second current carrying conductor, current is flowing in the downward direction. So magnetic field at point A, like this, it will be directed in the inward direction. Look, like this. So it will be directed in the inward direction, like this. It will be directed in the inward direction. So I am representing it like this. This is B2 vector and it is again directed inwards, like this. This is the magnetic field B2 at point A. B2 is the magnetic field due to the second current carrying conductor, right? Now observe the difference. Now what we are supposed to write is magnetic field at point A due to conductor 2, due to the second conductor. It is given by B2 is equal to mu naught. What's the current flowing through the second conductor? I2 divided by 2 pi r. And as we have discussed, students, direction of the current in the second conductor is downward. So applying thumb rule, right hand thumb rule, we get the direction of the magnetic field at point A to be inwards, right? So it is directed inwards. Clear? Now this first current carrying conductor will be under the influence of this inward magnetic field B2. So obviously it will experience a magnetic force. So therefore, conductor 1 under the influence of magnetic field B2 will experience a force given by F1 vector is equal to current element of the first conductor, that is I1L vector, cross, it is under the influence of magnetic field B2. And both are perpendicular to each other. B2 is directed inwards, current is along this direction. So the angle between these two is 90. So in magnitude, it would be I1L B2 sin 90. Isn't it? Substitute this value of B2 over here. What we get is mu naught I1 I2 divided by 2 pi r into L. Right? This is the expression for the force experienced by the first conductor. So what about the force per unit length? It may be represented by small f1. So f1 by L, it would be equal to mu naught I1 I2 divided by 2 pi r. So this is the expression for the force experienced per unit length of the first conductor, right? So both are exactly of the same magnitude, right? Let's find out the direction of F1 then. So, let's find out the direction of the magnetic force experienced by the first conductor under the influence of magnetic field due to the second conductor. So look, at point A, the magnetic field is directed inwards. Current is in the upward direction. So look, FBI. Magnetic field is inwards. Forefinger represents the direction of the magnetic field. It's inward. Central finger represents the direction of the current. So it is like this. Clear? Central finger, it represents the direction of the current in the upward direction. Forefinger, it represents the direction of the magnetic field. It's directed inwards. So thumb, it's pointing towards left. Right? So the force would be directed towards left. This is F1 vector. So students, what's the conclusion? Whether we consider the currents in the two conductors which are straight, parallel, infinite long to be flowing in the same direction or in the opposite direction, in both the cases, the force experienced by the conductor per unit length, it's given by this formula. F is equal to mu naught I1 I2 divided by 2 pi r. This is the basic formula, right? This is the first important thing which we have noted down. Second is, students, in case current is flowing in the same direction, then the nature of the force was found to be attractive. In this case, we have considered the current to be flowing in the opposite direction. One in the upward direction, I2 is in the downward direction. In this case, the nature of the force is found to be repulsive. So here, the nature of the force is found to be repulsive. And third, students, both are of equal magnitude. They are exerting equal and opposite forces on each other, isn't it? They are oppositely directed. So they form action-reaction pair. So these are some very, very important points which you need to keep in mind. Right, students? So we are over with case 2 as well. That is when the current flows in the opposite direction. Right? Now, let us use this definition, this mathematical expression, that is F equals to mu naught I1 I2 divided by 2 pi r. Let's make use of this mathematical formula so as to define the SI unit of current, which is ampere. Right? So let's make use of this particular expression. So what we have discussed is the force experienced per unit length of the conductor. It's given by mu naught I1 I2 divided by 2 pi r. Right? So these are the two straight parallel conductors. Suppose the currents are flowing in the same direction. So in that case, the nature of the force will be attractive. Just now we have discussed. And in case the currents in the two conductors are flowing in the opposite direction, then the nature of the force is found to be repulsive. Right? So, force per unit length, it is obtained to be mu naught I1 I2 divided by 2 pi r. Right? Now students, in case we consider the currents to be flowing in the two parallel infinite long conductors in the opposite direction, then also the expression for the force per unit length, that will remain same. So here, suppose the currents are flowing in the opposite direction. Only difference between these two is the nature of the force will get changed. In case the currents are flowing in the same direction, then the nature of the force is attractive, isn't it? And in case the currents are flowing in the opposite direction, then the nature of the force is repulsive. So in this case, the nature of the force is repulsive. Otherwise, the force experienced per unit length in magnitude, that will remain same. No doubt regarding this. Just now we have done both these articles, right? The mathematical verification part we have done just now. Okay, now our main objective is the third one. We need to define the SI unit of current, which is ampere, using this mathematical expression. And students, remember, presently we are dealing with the standard definition of ampere, which is the internationally accepted definition of SI unit of current. Current, as you are aware, it's a basic physical quantity in the SI system, and ampere is the fundamental or the basic unit in the SI system, right? So let's try to define ampere. What to do is, let's consider I1 is equal to I2 is equal to I, say, right? And let us also consider R is equal to 1 meter, and F, small f, as you remember students, it is the force per unit length, right? So force per unit length, suppose it is 2 into 10 raised to the power minus 7. What will be its SI unit? Newton per meter. So let's substitute all these values over here. Small f. Substituting all these values over here, what you get is 2 into 10 raised to minus 7. Mu naught, we are aware of its value, it is 4 pi into 10 raised to minus 7. It is absolute permeability of free space, isn't it? So mu naught is 4 pi into 10 raised to minus 7. I1, I2 each being equal to I, so it will become I square, divided by 2 pi, R is 1 unit. So what do you get? 2 get cancelled, 2 will be left, pi get cancelled, so 2 into 10 raised to minus 7, here 2 into 10 raised to minus 7. So what is left is I square is equal to 1, or I is equal to plus minus 1 ampere. So this is how 1 ampere is defined. Now simply what you need to do is, we will need to express these mathematical expressions, mathematical statements in terms of our own language, right? So let's try to define 1 ampere. Now look students, 1 ampere may be defined as that current which, when flowing through each of the 2 straight parallel infinite long conductors which are placed at a distance of 1 meter in air or vacuum, exert upon each other a force of 2 into 10 raised to minus 7 Newton per meter of their lengths. I repeat students, here we are considering the 2 conductors are to be placed in air or vacuum, and that is obvious if the currents are assumed to be flowing in the same direction, then the nature of the magnetic force must be attractive. While in case the currents in the 2 parallel conductors are flowing in the opposite direction, then the nature of the force is repulsive. That is there, no issues regarding that, right? So concentrate on the definition. 1 ampere may be defined as that current. Ampere is the definition, ampere is the unit of current. So 1 ampere may be defined as that current which, when flowing through each of the 2 parallel straight infinite long conductors placed in air or vacuum at a distance of 1 meter from each other, exert upon each other a force of 2 into 10 raised to minus 7 Newton per meter of their lengths. So this is the definition of ampere, right? Just try to just recollect the definition. I'm sure after understanding the concept behind it, you will be easily able to retain this standard definition of SI unit of current, which is ampere. 1 ampere, students, it is the current which, when flowing through each of the 2 straight parallel infinitely long conductors placed in air or vacuum at a distance of 1 meter from each other, exert upon each other a force of 2 into 10 raised to minus 7 Newton per meter of their lengths. And the force I am talking about may be of attractive nature or repulsive nature, depending whether the currents are flowing in the parallel direction or they are flowing in the opposite or anti-parallel direction in the two straight conductors. Clear, students? So, we are over with the third topic as well. So, students, I hope you have understood all the three parts of this particular session, right? So, that's it for this particular session. Stay blessed, stay happy, always be in jovial mood, and do join me in my next lecture then. Till then, bye-bye.